Hello, everybody. Welcome back. Today we're going to be looking at Unit 3.2, which is all about the properties of solids. So let's get started. So a lot of today's lesson is all about being able to categorize types of solids. Okay, and the first categorization of solids breaks them down into two categories. Here's the first, amorphous. Okay, if you think about what the prefix a or an means at the beginning of a word, it means without. Morph means shape, without shape. So some solids like glass, if you were to look at them at a microscopic level, they don't have any organization to their atoms and molecules, okay? We're not even really going to look at amorphous solids, much more than what I've just said. We are going to focus on the category of what are called crystalline solids, solids that do have some sort of arrangement pattern to their components. And just as an example, this is what a crystalline solid might look like under a microscope. Crystalline solids have organization to them, okay? And this is what I'm talking about. It doesn't have to necessarily be a cube on top of a cube on top of a cube, but it is some regular repeating pattern. Okay, now, within crystalline solids, there are four types that we're going to look at. Okay, here's the first one. Simple ionic solid. Any kind of ionic compound, okay, is an ionic solid. And when I say contains ions at the lattice points, okay, let's say that we do have a structure that is cubic, okay, cubes stacked on top of each other. Lattice points mean like the corners, the junctions, okay? If we're talking about an ionic solid, okay, these corners are the lattice points. And I would have like a sodium ion there, and I'd have a chloride ion there, a sodium ion there, and so on and so forth. A regular repeating pattern. And in terms of an ionic solid, I would want to minimize having like charges, like charged ions next to each other. So an Na plus is going to be next to a Cl minus, which is going to be next to another Na plus, and so on and so on. Okay. The second type of solid is a molecular solid. Another way to say that is a covalent solid, like ice or table sugar. Sucrose would be an example. Okay, now the difference here, they still have a regular repeating pattern, okay, but instead of having ions at the lattice points, let's say it's ice, we're going to have whole discrete molecules at every lattice point. Okay, and so on and so on. So unlike the ionic solid that had ionic bonds between the lattice points, a molecular solid, you know, what's existing between these two? Think about our last lesson. What holds two molecules near each other is intermolecular forces. Okay, that's an important distinction. What holds an ionic solid together is ionic bonds, very strong. What holds a molecular solid together is intermolecular forces. Okay. All right, here's our third type. A metallic solid. Anything on your periodic table that is considered a metal is in this category. Okay, we've talked about metallic solids a little bit before, so let's review. Metallic solids are going to be positively charged cations with their electrons flowing all over the place. Delocalized just means electrons that can easily move around. So metal atoms don't really hold on to their own electrons. Electrons are kind of shared all throughout a metal, and this is why they are such excellent conductors. And again, we've seen this phrase before. Metals have what we describe as a sea of electrons, electrons that can flow easily. The fourth type of solid is the one you might not be familiar with. It's called a covalent network solid. And these are atoms that are held together in some of the strongest bonds, okay, that exist. And we're going to talk about that type of solid in a little bit more detail in just a moment. Okay, so a lot of this is review. All right, ionic solids obviously are held together by opposite charges. The fancy term is electrostatic attraction. Okay, they have very, very high melting and boiling points because ionic bonds are very strong, hard to break. Okay, the ions repel each other. Let me say this first. Opposite charges attract to each other. Like charges repel each other. And this is the reason why ionic solids are very brittle. If you drop a big chunk of NaCl, table salt, and you drop it on the floor, it will shatter. And that's very brittle. And here's why. Okay, I know this is a little bit hard to see, it's kind of small, but if you make an impact, like you hit it with a hammer, let's say, okay, you have a chunk of NaCl and you hit it with a hammer, that's going to cause these ions to shift, okay, in this picture right here. And if you'll notice, let me change color. You have like charges next to each other. And do you think that they like that? They do not. Like charges repel each other, and you get this, what's called cleavage or breakage, okay? And it breaks very cleanly along these lines, okay? And so that's the description of something being brittle, and that's why ionic solids are so brittle. I think that's actually very cool. Okay. Ionic solids will not conduct electricity in their solid form. Let's review what you need to conduct electricity. You need charged particles. Okay, we got that. But they have to be able to flow or move around. And in an ionic solid, the ions are locked into that very tight crystalline lattice. So we've got charged particles, but they can't move. Now, if you melt an ionic solid into what we call its molten form, or you dissolve it in a cup of water, then you can get electricity to flow because the ions can move around. All right. Molecular solids, okay. This title on the slide in front of you, molecular solids without dipoles. That just means nonpolar covalent compounds. Okay, this is a little bit of review, all right? Solids that fall in this category, okay, I should say covalent compounds that are nonpolar are typically gases at room temperature, but some do exist in solid form. If you'll recall, something that is nonpolar is going to experience LDFs only, which are very weak. That is why most nonpolar covalent compounds are gases. They're easy to pull apart. Again, this is a little bit of review, but LDFs depend on the size of the molecule, the number of electrons. The more electrons, the stronger that London dispersion force is. Remember, the word was it's a very polarizable molecule. Okay. And this is why, as an example, the molecule iodine, okay, which is literally just two iodine atoms bonded together, okay, that's a nonpolar molecule. However, iodine is a large atom. Two iodines together have a great number of electrons. That is a very polarizable compound. And thus, even though it experiences LDFs only, the LDFs are relatively strong, which is why at room temperature, iodine is a solid. Whereas move your eyes up the periodic table in the same family, F2, fluorine is a gas. It's held together exactly the same way, but fluorine is a much smaller atom, fewer electrons, much less polarizable. Okay. Polar covalent compounds are going to experience dipole-dipole forces, not just London dispersion. Some of them are going to have hydrogen bonding as well. Okay, so your polar covalent compounds are going to have typically higher melting and boiling points because they are held together with stronger intermolecular forces. Okay, do keep in mind, guys, that no matter how strong the intermolecular force, that is still not even in the ballpark for how strong a covalent bond is. Remember the difference between intermolecular and intramolecular? Intra means a covalent bond. That's strong. But the forces between molecules are not nearly as strong. Okay? But when you have stronger intermolecular forces, we're going to have higher melting and freezing points, higher boiling points. Okay. Again, this is a little bit of review. Metallic bonding. Okay. Metals tend to be positively charged cations. Those little blue particles in the drawing, those are the free-flowing electrons. Okay. So let's talk about this fourth and final type of solid, which may be new to you. And carbon is a fascinating example of this. Okay. There are three different, the word is allotropes of carbon. That just means forms. Okay. The first form is coal, like charcoal, okay, which you can dig up out of the ground. Okay. Coal is an amorphous solid. It doesn't have any structure to it. There's really nothing to talk about chemically anyway, okay, structure-wise. So we're going to move on. It's boring. Let's move on. Diamond is another form of carbon. It is the hardest natural substance on Earth. It's an excellent insulator. We're going to talk about why. There is a third type, graphite. Okay. When you say pencil lead, it's not actually lead in your pencil. It's actually graphite, which is another form of pure carbon. And graphite has some really interesting characteristics to it. So we're going to talk about this. These are network solids, and they are connected differently, which is why we have these three different versions of carbon. Okay. Just before we move on, examples to know of some network solids. You need to know carbon diamond, carbon graphite, and very often compounds that involve silicon and boron, not necessarily together, like compounds that have silicon in them, compounds that have boron, those are very often network solids. Like silicon dioxide, that's quartz. Okay. So guys, microscopically, this is what a diamond looks like. All right. This goes back to our last unit. They are tetrahedrally linked carbon atoms. They have sp3 hybridization. They are held together with sigma bonds. And all of this huge network of carbon atoms and bonds is incredibly strong, which is why diamonds are the, again, hardest natural substance on Earth. Okay. I said they are also excellent insulators. Remember, to be a good conductor, you've got to not only have charged particles, but they have to be able to flow. Diamonds do not have any room for electrons to flow. It's such a tight network of atoms, there's no room. So diamonds are excellent insulators. Starbucks should capitalize. They should make all of their travel mugs out of diamond. We should all be living in diamond homes. We'd be nice and warm in the winter. I mean, aside from the cost and all that, you know. Okay, now graphite is interesting. Graphite is made of carbon, but it's not this tightly bound network. Graphite is laid out in these sheets of carbon, okay? And each carbon is not sp3 hybridized, it's sp2 hybridized in a trigonal planar arrangement. And we get these flat six-membered rings that fuse together and they form these planes, these sheets. And these red dashed lines in the drawing, those are the connections between the sheets. Those are pi bonds. So there's sigma bonds holding the atoms together, but pi bonds holding the sheets together. And what ends up happening, guys, is these sheets can slide past each other pretty easily because the pi bonds are relatively easily broken. And so graphite, if you've ever, some of you that are artists may have worked with powdered graphite before. It's so weird. It's a solid, but it's like a slippery solid. I know that's really weird to describe a solid that way, but you get some on your hands and your hands almost feel like wet, even though they're not, because those sheets literally just slide past one another. And when you write on a piece of paper with your pencil, you are literally leaving, you know, thousands upon thousands upon thousands of those sheets on the paper. Okay. Now, graphite, unlike diamond, this is just another view of those graphite rings. The layers slide by each other and there is room for electrons to move around. So graphite is a good conductor. You do not want to put your pencil into the electrical socket because it will conduct beautifully. Please don't try that. Okay? But between the rings, there's room for the electrons to move around. So it's just another example of a network solid. So what I would like for you to do at this point is to identify what of the 4 types of solid do you have for each example here. Is it an ionic solid, molecular solid, metallic solid, or network covalent solid? So pause the video and see what you can do. All right, let's see how you did. Hopefully you can read my handwriting. So remember, molecular just means covalent. So if you see two nonmetals, you know it's covalent. Silicon dioxide is a network solid. Remember I said a lot of compounds that involve silicon or boron are often network covalent. Tin and chromium are metals. And potassium bromide and sodium hydroxide, those are definitely ionic. Okay, so sometimes you'll see questions that are like multiple choice that'll ask you to identify what type of solid you're dealing with. All right, let's look at 2 more questions for practice. It's a multiple choice question. This one says, which of the following diagrams best illustrates how a metallic solid is malleable after a displacement? If you guys will recall, malleable just means a material that you can bend it, so it's not brittle, it doesn't shatter, it doesn't shear off, it's just bendable. All right, so pause the video, see what you think. All right, so hopefully you guessed C as your answer. Okay, C is the answer. All right, letter A is showing us an ionic solid, that process of right before an ionic solid would shear apart. Okay. B is not really showing us anything. C is our answer because remember what we said about a metallic solid. It's a group of metallic cations. So that's where all those pluses are. And just those electrons are kind of floating around between the ions. And you can see right here, okay, that it's sort of been bent a little bit. In letter D, to me, looks like a protein or a polymer or something. That does not look like a metallic solid. All right, one more. A student finds a bottle of magnesium chloride and hypothesizes that the solid is a good conductor of electricity because it contains magnesium, which is a metal, and all metals are good conductors. Do you agree or disagree with the student? Justify your claim. So pause the video and think about it. Let's see what you think. Okay. Hopefully you vehemently disagreed with the student's claim. Yes, the compound contains magnesium. However, the compound has magnesium ion in it. Okay, magnesium metal, pure metal, is a good conductor, but magnesium ion, when it is locked in that crystalline lattice structure, which ionic compounds are, there's not going to be any electricity conducted because those ions are held together so tightly. They can't flow, they can't move. Electricity is not going to be conducted in a solid ionic compound. Just to refresh your memory, if we were to melt that ionic solid into molten form or dissolve it in water, then it could conduct electricity. Okay, but magnesium ion and magnesium pure metal, not the same thing. So that's it for properties of solids. I hope you've learned a little something today, and I look forward to seeing you next time.